Hi guys, in this video we're going to talk about how to draw particle diagrams to help you think about limiting reactants in a chemical reaction. So what we're going to be doing is looking at some questions, sample questions, and drawing some particle diagrams. So let's grab our Cornell paper. So let's fill this out. Here is where your name and the class period and today's date go. Over here in the objective box we are going to put our objective, which is objective 3, limiting reactant diagram. So we're going to be drawing our particle diagram. So let's come up with an essential question. How can a particle diagram help determine a limiting reactant? Now the unfortunate thing about this question is that there's a whole lot going on when we talk about limiting reactants in these particle diagrams. So let's talk about what is a limiting reactant. Well, a limiting reactant is whatever you have less of. Well, it might be what you have less of. Sometimes you have more of it. Either way, it's what you run out of first. So in the framing questions, you answered a question about bicycles. If you have so many wheels and some seats and some bicycle frames, how many bikes can you make? And you might have tons of wheels, way more than you have frames, but if you don't have 2 wheels per bike, then you might run out of wheels before you run out of frames. So sometimes that happens in chemical reactions. So the limiting reactant is the reactant that you run out of first. So during a reaction, it is consumed first, you run out, and then your other reactant will end up as a leftover if you have any still in the jar. This is why when you're doing a chemical reaction between 2 substances that make something yummy in the end, you probably don't want to drink it because there might be some leftovers of one of the reactants in there that is definitely bad for you. So let's get a sample equation and see what these particle diagrams are going to look like. So here's our equation. P4 plus 3O2 gives 2 P2O3. So this is a synthesis equation in which our phosphorus and our oxygen are coming together to make this diphosphorus trioxide. And when we draw our particle diagram, we need some boxes. We need to know what we're starting with. So let's get our sample question. If 5 particles of P4 and 8 particles of O2 react, what is the limiting reactant? Now you might look at this and you might think, hey look, I have 5 and 8. Obviously I'm going to run out of 5 first. But in the chemical reaction we have to pay attention to the coefficients. So there's a 1 here and a 3 here. That is important for us to note. So when we draw our diagram we'll see what we run out of first. So let me scroll up and let's get our boxes here. So just like we were drawing particle diagrams in our last unit to show that mass was conserved, now we're going to show what happens if we have more of one or more of the other. So we're going to use the same idea. So I'm going to make a key over here, and maybe I'll make my P's triangles and my O's circles. I think that'll help me keep them separate. And I have 5 particles of the P4, so I need 1, there's 1 P4, and 2, and 5, and so they all have 4 P's in them. There's my 5 particles. So then I'm going to draw my oxygen. It says I have 8 particles of the O2. 1, 2, 8. And now what I'm going to do is I'm going to look at my products. So over here it says I've got P2 and O3. So let's see, this might be hard to keep track of. So I've got to make sure that I have the same number on both sides, just like I did in the last unit. I'm just starting with a different number. So let's see, here's 1 P2O3, and here's another P2O3, and then let's do some counting here to see what we'll have left. So let's see, I'm going to use my handy little highlighter tool. So I used 1, 2, 3, 4, so that made me use up one of those, and then I've got 1, 2, 3, 4, 5, 6 of the O's. 1, 2, 3, 4, 5, 6 of the O's. Okay, so then I'll keep going. Let's see here. 1, 2 P's, 1, 2, 3 O's, 1, 2 P's, 1, 2, 3 O's. So let me highlight those again so that I can keep track of what I'm using up. So 2 P's, 1, 2, 3 O's, 2 P's, 1, 2, 3 O's. So if you look here when I'm about to add another one, and I'll highlight them in yellow, if I do another 2 P's and 3 O's, I'm going to end up with half of a P4 particle and half of an O2 particle. And I can't have halves of particles. I have to have the same particles. So what I'm going to do is I'm going to stop there. So that's all the reactants that I can have. Are all the products that I can have, and the rest are what we call leftovers. So I'm going to draw those over here unchanged. So I have 3 of the P4s, one more P4, and I have 2 of the O2s remaining. So if I do a little bit more highlighting here, so I couldn't get, whoops, that's not highlighter, I couldn't get all of these into a particle. So these guys end up being my leftovers. And I forgot to highlight these here. So the reactants and the products and then the yellow stuff is my leftovers. So when you're drawing the diagrams, that's all you do. You figure out how many you can make without leaving any pieces. So you might want to write that down somewhere. So we're going to sum it up here. Let's look at our first point. Draw your diagrams like you're going to balance the equations. And then the next thing you want to make sure you do is don't split up the particles. If you don't have enough to get rid of all of it, just like when you're doing the moving of ions and bonding of things, don't split it up, okay? So if you can't make all of the particles into new particles, then you'll just have to leave those alone, and then those become your leftovers. You may end up with leftovers, and that is perfectly okay. So when you're drawing these pictures, that's how you do it. If you have any questions, make sure you ask for clarification. I'll be happy to run through some more examples with you.